Okay, so a couple more definitions to go through, kind of move through these. So we have our spectral directional emissivity. We don't always want to concern ourselves with like every wavelength, every angle that's possible. It's just too much to worry about. So sometimes we'll start simplifying this stuff down. So there's another definition called hemispherical emissivity. Okay, and hemispherical emissivity is now, we're going to drop any angular dependence, or we're going to say integrate it, right? We're going to integrate that into a single value. And now we'll just describe the emissivity purely as a function of wavelength. So this would be epsilon lambda, and that's going to be emitted radiation. And the units on that are just watts per meter squared micron, right, as opposed to per meter squared micron steradian. Now it's just per meter squared micron. Emitted radiation divided by the emitted black body radiation. Again, with the same units, watts per meter squared micron. This lets us take away that dependence on angle. So it lets us maybe simplify, express it in a way that takes away that dependence. If we maybe plot what this might look like for a real surface. So you have, let's say, some emitted power, let's call that capital E lambda. And let's plot as a function of wavelength lambda. So if we have our black body curve, the black body curve looks something like, I don't know, like this. For what we're saying here is that you can pick a given wavelength here, and then as a function of that wavelength, take off part of what the emitted power is, and that's your real surface. So it might look something like, your real surface might look something like, this or whatever. So then if we actually plotted our emissivity as a function of wavelength, emissivity lambda as a function of wavelength. In this example, I guess here I've got a huge loss. Here it's maybe a little bit less, and here it's sort of approaching the real surface. So if I plotted that, it might actually look something like this, something like that, where this is 1, and this is the real epsilon lambda. So the point I'm trying to make here is that for a given surface, you can still represent the emissivity as a function of wavelength, and it doesn't have to be just one value, right? It can depend on the wavelength. And every real surface has some dependence. Okay. Okay, so then let's go another step further, and you can bring all this stuff together, and then it's called the total hemispherical emissivity. So total hemispherical emissivity, that is what we call just plain old epsilon. So that's what we've seen so far. Every time maybe the handful of times I've given you a problem that has emissivity in it this semester, it's been, okay, assume emissivity is something, right? And then that becomes the thing you multiply in the radiation equation. So this total hemispherical is the thing we've been talking about, and that again is just the emitted radiation, and that is units of watts per meter squared divided by the emitted black body radiation of the same units. Okay, another definition of this, and the actual formal definition of this, is to say epsilon is equal to the integral from 0 to infinity of the emissive power, E sub lambda, d lambda, divided by the black body, which is sigma t to the 4th. So graphically, I guess, you can understand what we're doing here. We're saying we have, again, our black body curve. It looks like this. We have our real surface curve. It looks like this. So we're just taking the integral of this. Right, that's up here. and we're taking the integral of this. That's down here. And that gives us our total emissivity, total hemispherical emissivity. Okay? So those are kind of just the basic definitions there. The only thing you have to remember is, don't confuse the total hemispherical with just spectral emissivity, all that kind of stuff. Just keep them separate. Okay, so then let's see. How to actually compute some of the, like if you need to go through and evaluate what these, let's say you're given like a spectral emissivity curve, and you want to then evaluate what's my emissivity or my emitted power given that I have some emissivity curve, right? It's not just as simple as saying, like up here, if we were to start and say, I've got some plot again, let's take that, let's do this better. Let's take that plot of emissivity, which is a function of wavelength, and let's say our surface looked like this again, where this is the value 1 up here. So that's our real surface. If I want to go and evaluate like the emitted power from an actual surface, I can't just go and take the average, like the average of this function and plug that in. It's going to actually depend on the temperature of the surface as to what the effective emitted power is. And you have to maybe think about why that's the case. So if I also plot out down here a bunch of black body curves as a function of wavelength. So this would be in, let's say, micron. And I want to plot the black body power. So that would be EB lambda. If I am a surface that's emitting at a very, very high temperature, let's say it's the sun, right? The sun is emitting, and it is going to emit a black body curve that kind of looks like this. This. So if I match that up wavelength-wise, it says that the sun is trying to emit a bunch of power at a pretty low emissivity. Okay, if we're the Earth and we're much cooler than the sun, our black body curve probably looks like this. Okay, so the Earth is going to be emitting in a wavelength range primarily that's pretty good for emission. Right, so you have to take into account the fact that the surface of the emitting body, the temperature of the emitting body is really important in evaluating the effective emissivity. So the way that we would do this is simply to say that, okay, we had our equation. Let's see, we had our equation. Let's go epsilon lambda. Epsilon lambda is defined as E lambda divided by E B lambda, which we can also write as, if we then integrate this, we can write it as the following, which we had on the last slide, integral from 0 to infinity of E lambda d lambda divided by sigma t to the 4th. So what we're saying here is, if I'm going to do this, I need to come up with an expression for this piece here. Well, I know that this relationship, there's a relationship between E lambda and the emissivity as a function of wavelength and the black body emissivity, which we know just based on Planck's law. Okay, so we can take this piece up here. I think I said we rewrite it, but what we're actually doing is we're taking this piece up here, solving for E lambda and subbing it in here. Okay, and when we do that, we end up with the following, which is epsilon is equal to the integral from 0 to infinity of the emissivity function of wavelength times the black body power at that wavelength, d lambda, divided by sigma t to the 4th. Okay, so that's maybe a long way of saying if you're trying to establish the emissivity and you're doing the integral, all you got to do is take this curve and plug it in to this integral. All right, but maybe you understand why. One kind of interesting point, and maybe it is something you've seen before, but when it comes to like the practical applications of this, obviously every real surface has things to think about here. But for like the biggest problems that we're facing, this is the core of it, right? So climate change, this is the core of it. You have something that's emitting the sun at one curve. You have the Earth that's emitting at another curve, and they're different. And so anytime you have something, I'll say in between those two bodies that have some different spectral properties, it's going to affect the rates at which it's emitting. So if you look at like the CO2 in particular, you can look at CO2. CO2, let's say, has these bands, right? These bands where it absorbs. And it's because the molecular structure of CO2 is such that it interferes really well with certain wavelengths. Right? It's just sort of the shape of the molecule, the size of the molecule. It interacts with certain wavelengths. Those wavelengths happen to be like here. So you have like a chunk here, you have a big chunk here, a bigger chunk here, a bigger chunk like here. Okay, so if this is our CO2 emissivity, right, that's saying it's absorbing at that wavelength, sunlight gets through really well. It turns out that at our 300 Kelvin curve, I should maybe label this. Let's say this is 5700 K, that's the sun. This down here is about, 298. It's about the average temperature of the Earth, I think, if I can remember that off the top of my head. This curve has the most power emitted right where CO2 loves to absorb, which sucks for us, right? So how does this system compensate? If you're absorbing energy that's being emitted and it's being reflected back to the Earth, what has to happen? This curve has to shift. The same amount of power has to get out. So the curve has to shift this way. And by shifting this way, remember Wien's law. Wien's law says that temperature is going to shift that way, right? So basically the equilibrium is changing just because of the spectral dependence of a particular gas in our atmosphere. Right? So it's kind of relevant, interesting, important for us to understand. All right. Questions on that? Okay. Sorry, one other thing. So you can, I just have this note for ease down here. So you can go for different properties for typical engineering problems. If you want to know what the emissivity is for typical stainless steel polished or something like that, you can go and look it up in ease. I won't show it. It's just a table, but it has a bunch of information. Maybe not as much as you'd like sometimes, but it has a good set, I'd say, of surfaces. One thing that you want to note is it's not just like the molecular makeup of a surface that's important. It's also its finish. So if you have a really rough surface that's steel, carbon steel, even if it's a carbon steel, it's going to have a different emissivity than a really highly polished surface. And part of the reason for that is like the little microstructures on the surface can physically interfere with emitted radiation, and that just changes the properties a little bit, right, as far as we're concerned. So anyways, you can go look it up in ease. There's other places you can go find that information. Okay, let's see. So what we're going to do for our problems is not necessarily focus too much on like continuous functions of emissivity, which depend on wavelength. Instead, what we're going to do is make some simplifications so that we can come up with systems to solve these equations. So let's say we had our curve up here, our diffuse curve. Our diffuse curve kind of looked like, or our directional curve kind of looked like this. Came back here. So that's fine. I guess you could maybe with a ray tracing program you could model this or something. But actually, what we're going to do is, for most cases, we'll just assume that it's what's called a diffuse surface. So you'd take some value like this that is effectively representing the directional average, and we'd use that instead. So this would be our diffuse approximation. So that's saying if you're a photon that's emitted, you have an equal probability of being emitted in any direction. In this case, in the direction theta. So it's diffuse. It's also diffuse in the circumferential direction. So that's a really common assumption that's going to be made. Obviously, it's not quite right because you have this going on at the edges, but for most situations, you don't really care about that too much. So that's one assumption. The other assumption that we can make is we could take our surface, which had this, again, this kind of curve for emissivity. Emissivity is a function of lambda. And we can just represent it as a gray surface. So we would say this is going to actually have, okay, maybe we go through that integral and we decide that at the temperature we care about, we're going to model it as a flat line. So there we're saying that this is actually a gray surface. Now, again, I'll caution you, can't just take the average, right? Do it for the temperature you're going to be working in. But what I am saying is, let's just assume that we went through that process, took the integral over the right temperature range, and in that range we're going to say it's this value, this gray value. So why, by the way, am I calling it a gray surface? Well, if you have emissivity up here, this is black. If you have emissivity down here, this is white. If you have this curve, this is saying it's preferentially emitting or then reflecting light at a particular wavelength. So if I happen to preferentially emit in the green range, let's say, or preferentially not emit in the green range, that means it's reflecting. So it's going to look green to us, right? If it's flat all the way across, there's no dependence on wavelength, so it's actually like visibly gray. It appears to us as gray. So there's no dependence there. So that's why we call it a gray surface, and it's gray because it's between black and white. Okay, so that's one assumption. This would be called the gray surface. The other thing we could do is if we weren't happy with this, let's say we don't actually know we're at the temperature range quite right. We know that there's some system of equations we're going to solve for temperature. We can do this semi-gray approach. So that means I'm going to take a segment here, and I'm going to represent the emissivity just with a segment of a gray, spectrum. So it might look like this here, and then I'm going to look again, and then I'll do it again up here like this, and then like this, and then like this, and so on. And so you're covering these intervals like this with unique values. It means that then you have to do a separate energy balance for each of these ones on a given surface. It makes it more complicated, but it lets you get kind of a better estimate of the performance of the surface. So this we'll call semi-gray approximation. So we'll try to do, or at least talk about both of those in the class here.